Thank you so much for this invitation. I'm really excited to be here. Today, I'm going to be talking about work that I did almost 3 years ago now as part of an internship at NASA's Jet Propulsion Laboratory. It's on the unsupervised detection of magnetic field boundary crossings in the goal of responsive instrumentation. And this is work done with Kiri Wagstaff, Gary Doran, Cody Cochrane, Katrina Jackman, and Abigail Reimer, all wonderful people to work with. So some context to our problem. The Plasma Instrument for Magnetic Sounding, or PIMS, is an instrument on the Europa Clipper Mission, which is going to be launching in 2024. Yay. And it's going to be studying the properties of the plasma around Europa and Jupiter. Europa is one of Jupiter's moons. It's widely believed to be, one of the potential candidates for life in our solar system. So it's a very exciting mission. And this mission, Europa Clipper, is going to be the first to kind of study Europa and give us a lot of cool insights about what happens there. About PIMS, PIMS counts the number of particles within ranges of energies. So the particles that are part of the plasma. And it'll operate in 4 different modes with different sampling rates and different energy ranges. The reason for this is that due to radiation sensitivity concerns, Europa Clipper is not going to be orbiting around Europa, but it's going to be orbiting around Jupiter and make regular flybys. So depending on how far Europa Clipper is from Europa, PIMS will be operating in different modes because the electromagnetic environments are very different as you go away from Europa. So in particular, there are the survey, magnetospheric, transition, and ionospheric. And the current mode switching logic is completely prescriptive. It's based on estimates of where these regions lie. And these estimates are, they're not, they're kind of like guesses that domain experts have about, what mode we should be in at what distance. The question that we have raised in our research is, can we detect these transitions between the magnetic field regions automatically? And can we do this in an onboard setting so that we can have this real-time instrument adaptation? So that explains the responsive instrumentation part of my work. So what do PIMS data look like? At each time step, PIMS will record the number of particles collected in energy bins. So each bin is like a sub-range of energies. But PIMS data doesn't exist yet, right? Like this mission hasn't done. So we look at some analogous instruments from previous missions, and especially the Cassini mission, which is super successful on its mission to Saturn. And especially we're going to be focusing on the electron spectrometer on the Cassini mission. The design of these instruments is quite different, but the phenomenon and that they'll be capturing are quite similar. So we felt that this is like a pretty good, this would give us a pretty good understanding of the kind of methods we can explore. So if you look at CAPS-ELS data, of which the Cassini mission started in 2004, and CAPS lasted until 2012, we have this huge resource of data, and you can think of each observation, each 6-hour observation that CAPS takes, as a multi-dimensional time series. So here's an example. On the x-axis, we have time. On the y-axis, we have the different energies, and each kind of rectangle is like a bin. So at each time step, CAPS-ELS will sample a full sweep of along the y-axis, a full sweep of energies, and it will record at this energy I captured these many particles, and that's indicated by the color. And we seek to kind of identify Saturn magnetopause and bow-shock crossings. These are basically interactions between Saturn's magnetic field and the solar wind. And these are basically events that kind of are analogous to what we would want to detect in the Europa setting, right? So here's an example. Over here, we can see like there's a shift in the energies as through the magnetopause, and there's like a corresponding downshift from the bow-shock later. So these two don't have to happen like in the same 6-hour window. They can even be multiple magnetopauses because of the spacecraft trajectories. And so there's a lot going on here, right? Like this data is inherently quite noisy. But what are the advantages of responsive science, right? That's kind of our case here, is that many of the phenomena that we're trying to understand better are already like quite poorly understood. In particular, for Europa, the magnetic environment and the regions, they're not very well understood. They haven't been studied before. And so using these methods can actually help pinpoint, the boundaries and say that, maybe we should have been in this mode when we were in this mode. And that can actually, kind of improve, give scientists, multiple, interesting phenomena to look at. Here are two examples of things that we would like to capture. These are, very important scientific discoveries from the Cassini mission. First was this existence of these high energy electrons near Enceladus. That is one of Saturn's moons. Over here, you can see kind of in the middle, you kind of see a bunch a bunch of electrons here with high energies. And this was pivotal to kind of understanding the electrodynamic coupling between Saturn and its moon. And this is one of pretty breakthrough finding. Another example is these negative ions that was captured by CAPS near Titan. Titan is another of Saturn's moon. So we want to kind of have responsive instruments that are in the right operating mode to capture these events, right? Because these are this is why we do science. And so having these kind of algorithms that can automatically adjust the mode of the instrument can enable this sort of discovery. Okay, so why is this hard, right? First thing is that we have a severe restriction on the computational resources on the aircraft, on the spacecraft. In particular, we have a 130 megahertz processor. This is because of radiation sensitivity concerns. We would like to have a lot more, but this necessarily restricts us to very simple methods. The boundaries between these magnetic regions are not sharp. They're very diffuse. There's a lot of complex phenomena going on there. Especially in CAPS data, finding the magnetopause is very hard. In particular, the experts tend to use data from other instruments and kind of combine them all together and say that this is a magnetopause, this is a Bosch-Hoff, and so on. So previously, all of the identification of these crossings was done mostly manually. So this is having something that can work automatically is a huge breakthrough. Within the region too, there are many local variations. Some of them are for example, these phenomena that I showed, these negative ions, these high energy electrons. So we would want to capture those, but we don't want our detectors to say, I'm actually in the wrong mode when I'm actually just seeing some of these local variations. And perhaps most importantly is that the spacecraft trajectory variation as the mission progresses. So Cassini, it doesn't take the same orbit, right? There's been a shift in the orbits around Saturn, and that leads to different angles of interaction with the boundaries. We don't directly tackle this in this work, but I think this is a really exciting to kind of go from the first principles approach and kind of model these boundaries better. I would say that's a very exciting direction for future work. Okay, so what we understand that Cassini data, this CAPS data can be represented as a multidimensional time series, one dimension for every bin that one energy bin for that the instrument is using. And we have these restrictions on simplicity in the sense of computational reasons. But the advantages of casting it in this time series framework is that we can build off on the huge amount of time series literature that people have been looking at and researching on for the last 100 years or so. So we selected a bunch of methods that all do very different things. I'm not going to go into details of all of these methods. Some of them kind of model the observations as being emitted from some hidden states. Some of them kind of do density ratio estimation. So if I have a set of observations I took now and a set of observations I took 5 minutes later, how different are they in terms of some sort of probabilistic divergence? Some of them, the last two here, SATS and the matrix profile, they are actually based on simple, not exactly simple, but nearest neighbor distance. This is not simple in the time series context because you have to avoid self matches in that you should not be comparing your nearest neighbor distance to something that is to a subsequence that overlaps with you, because that tends to cause something called trivial matches. I'm not going to go into details of these algorithms. I'm just going to show you some nice pictures. So in particular, the matrix profile is a pretty popular method to kind of compute these nearest neighbor distances. One of the key innovations that we created, extensions that we proposed, was a multi-dimensional variant of this. There have been some of these before, but they all used to they used to kind of work badly to find discords. Discords are subsequences, time series subsequences that have high nearest neighbor distance. So we explored a bunch of methods, and it turned out that kind of just computing this summed up matrix profile that works really well. And get more details in our paper. So here's an example of the multi-dimensional matrix profile on the CAPS-CLS observation of Titan that I showed you before. It's a bit zoomed out to show how much this entire 6-hour period. And these are kind of the scores that it assigns, and we see that close to the occurrence of negative ions, the scores peak, which is really good. This is what we want. There's no, I have not like any kind of tuning and all. This is just an example. You can obviously kind of tune this to get even better results, but yeah, this is just an example of how the multi-dimensional matrix profile can be really used to kind of extract such anomalous time series subsequences that maybe scientists should take a better look at, or maybe we should down like certain observations. Okay, so here's an example of how we of the HMM models and how we kind of evaluate it. So what happens is the HMM kind of segments the time series on top into kind of two parts. So there's two states, and it thinks of every observation as being emitted from these latent states. So you see, it actually does a pretty good job. So each of these kind of wherever you can see the green and yellow switch is actually it actually quite matches the transitions really well. And we convert the HMM states to kind of output a score from 0 to 1, and that allows us to basically threshold them. The score is based on the kind of the estimate of the probability distributions, and these scores are thresholded, and then we can compare them to domain expert labels, and we can compute like we call a precision, which basically says how good is your algorithm doing in terms of false detections and true detections. Yeah, so this is kind of how we evaluate all of these algorithms. We basically optimize them on, we basically choose the hyperparameters. So all of these methods work in the unsupervised setting. They never actually see the true labels. We only tune the hyperparameters on data from 2004, which is a very, very small subset. And we actually evaluate them on data from 2005, 2012. So like in the forward, in data from the future, which is kind of like how these are going to be used in the operational sense. And we find that, the Bauscher crossings can be identified really, really well. In fact, the matrix profile extension that we propose actually performs the best. Ideally, we want to kind of optimize for precision. So like we don't want to be having too low precision, because then we're having too many false positives, and that kind of, kind of really hurts the operational feasibility of these algorithms. So on the Bauscher crossings, we do really well. In the magnetopause, we find that the performance is not as satisfactory, and we leave this as kind of like future work. Like what are the kind of things that we can do? We have some ideas there. But yeah, I think this is like super cool. Like we were like pretty. We actually found by doing some more deeper analysis that there might be some error in the labels themselves. Katrina was really helpful. Katrina and Abigail, I remember, were really, really helpful with kind of doing like a deeper analysis. We found that certain false positives may not actually be false positives at all. But yeah, there's obviously limitations to any sort of labeling. Okay. So, yeah. So we also, so this is evaluation over all of the years. We find that the performance actually depends quite significantly on, for all of the algorithms, actually depends quite significantly on the kind of the local behaviors, in some sense, that the exact spacetime trajectory that is chosen. So we see that some years performance is really good, like in 2008, whereas in some years performance actually struggles a bit. So I think understanding, kind of doing this kind of dynamic adaptation based on kind of recent data. So like suppose you're operating in 2006, and you want to kind of maybe we shouldn't be using parameters from 2000 that you've optimized for 2004. Instead, maybe you should like look at samples and kind of optimize over those samples, like a continuous fashion. But yeah, this is definitely like we notice this behavior across algorithms, so it's clearly something that the community can take up as a challenge. So we went one step further. We actually implemented these algorithms on a PowerPC board, which actually quite mimics what's going to be deployed uh, on a spacecraft. So it kind of gives us a more accurate picture of, what are the computational resources that we have and are they enough? So in particular, these results that I'm showing you are for like the baseline, but they kind of scale up well for the other methods as well, based on some empirical calculations. So we actually, these previous results were kind of like Python implementations, right? They're not really realistic of what we're going to do on board. We actually implemented this in C with like, following, like flight code standard rules and all of that. It was pretty interesting, like designing the whole system from scratch. And we found that given like the fastest sampling rate from PIMS, which is like one observation every 500 milliseconds, we find that we are, for even if you're doing like this median filtering, pre-processing and so on, we can take at max 10 milliseconds per observation, which is super, super fast for the baseline method, and correspondingly, like the more advanced methods also can be done with pretty fast. The memory usage, as I talked about, this is the other aspect of computational resources. We can't use more than a few megabytes on board, which is quite restrictive. Even with the median filtering, we can filter against the last 100 observations, and we only need like reasonable 25 kilobytes, which is not much at all. Obviously, the data type that you use to represent these matters a lot in terms of your memory usage. Another really, really interesting analysis that we did, we actually investigated how these algorithms perform when exposed to radiation. So I talked about why Europa Clipper is going to be orbiting around Jupiter is because the radiation near Europa is really, really high. And so to extend the lifetime of the mission, they choose to orbit around, make like, larger orbits around Jupiter and just make fast flybys of Europa. And that allows the mission to last for many, many more years. So we actually model like via simulations, this tool called bit flips, which basically allows exposing parts of our memory in our C code to single event upsets. So here's an example. So this is suppose an array. A single event upset is basically the flipping of this bit from 0 to 1, just based on this cosmic radiation. And this cosmic radiation basically corrupts the data. So the CPU basically sees corrupted data, and that obviously will degrade, the performance of the algorithm. And you need to be really, really sure that your algorithms are robust to this kind of radiation. People really haven't studied this setting before at all, because this whole setting of like onboard data analysis is quite new. So our work, this is led by Gary, and this was recently actually published at IEEE Transactions, Aerospace Systems. And so here are some results we actually analyzed a bunch of algorithms across a bunch of instruments, not just PIMS. I'm just showing you the PIMS results here. And we see that, the average precision, which is kind of like a metric that we use to kind of compute, to kind of summarize the performance of an algorithm, it actually degrades as the radiation increases. So it goes from like 0.2. As I said, I mean, the average precision is probably not the best metric for our purpose because we're only interested in the high precision domain range. But this is just like it's a good way of just summarizing, how does the performance degrade over as you increase the radiation rate. So on the x-axis, the fault rate is going from 10 to the power minus 18 to 10 to the power minus 3, actually a little bit more than that. But we see that the performance as for different random seeds, this is pool over different random seeds for affecting which part of the memory gets affected. And this happens at every single instruction. So it's a little bit expensive to kind of simulate this, but it doesn't take too long, luckily. And we actually find that, unexpectedly, the implementation of the median filter in this current form, it doesn't improve robustness. What the median filter does, it looks at previous observations, and you would say that, since we're doing like a median filter, these single bit upsets, maybe this can be kind of filtered out. But the thing is that the computation of the median filter itself actually has additional instructions, right? And that actually it becomes like a trade-off, and it doesn't seem to give us much or any benefit with respect to robustness to radiation. But the good news is that despite all of this, we're actually quite robust. So the expected fault rate is only 10 to the power minus 19. We don't see much significantly degraded performance until 1,000 times more radiation than that. But this is like only for the baseline algorithm. It's still interesting to see this for other algorithms as well. Okay, so some future work. We talked about unsupervised methods that can basically automatically kind of identify these transitions without having any labels. But often we would, if you're just interested in maximizing the performance, then can we just maybe label a subset of the data and just kind of fine tune our parameters on those. Like for example, for the first few flybys of Europa, that would be super cool to see. Another thing I talked about was that can we have online adaptation of these parameters, which would kind of handle these observations in a streaming fashion, and then you can adapt your parameters to accordingly. But yeah, I think this is like a really exciting domain, really exciting space. There's a lot of things to be done here. Yeah, I think for more detail, I've gone over like a lot of things. Our computer and geosciences article was recently published a few months ago. We actually also released our pre-processed data, so you can easily kind of look at all the Cassini crossings, and also a code for all of the algorithms and the pre-processing pipelines. That's also open source. And there's also our IEEE transactions paper has also been recently accepted, although it hasn't been formally published yet. But yeah, I think this is really exciting. We'd like to thank a lot of people for this. The Europa Clipper Mission, like all of the teams working behind that, who very useful feedback. Many of the high performance computing resources from the JPL side were very useful. And finally, like the Caltech Surf Fellowship for funding. All right, thank you so much.